Hello, welcome back, everybody. Today in calculus, we are looking at section 11.6, which deals with absolute conditional convergence and also the ratio test. So the absolute and conditional convergence is really just kind of like a form or a way to actually prove the bigger one, which is the ratio test in this case then, okay? So let's go ahead and begin. First of all, we need to define what is an absolute convergence, or what does it mean to have a series that's absolute convergence. Also, what does it mean to have some series that is going to be conditional convergence? So here we go. Underneath right here, these are going to be the definitions then. So if you have a series right here, we'll call A of n right here. We're going to see that it is absolute convergence if the series of the absolute value converges. So that means that if you have a series and then you take the absolute value of all of the terms and then you're going to add them all up, then if that converges, then it is considered absolute convergence. So giving a few examples of some that are absolute convergence, it'll be something like, say, this guy over here, because if you take the absolute value of it, then you're technically going to get the same thing. And then you can then take the top part, which is going to be less than or equal to 1. And so if you do kind of like a comparison test, then it is going to be less than or equal to the summation of 1 over n cubed, and by the p series test, and therefore it is going to be therefore it's going to be convergence. So because the absolute value is convergence, then that means that it is A of n is going to be absolute convergence then. Another one that is going to be absolute convergence is if you have something like this guy over here, where if you take the absolute value of it, you'll notice that what goes away will be the alternating part. And that gives you the summation of 2/3 raised to the power of n minus 1. And in this case, that is also going to be convergence because of the geometric series test and because your ratio is less than 1. So these two would be examples of a series where it is absolute convergence then. Now, the term conditional convergence is a little bit different, but it's almost kind of a little bit similar. So we say that a series is conditional convergence if the original series converges itself, but the absolute value of the sequence, and then if you make it into a series, that actually is going to diverge. So over here are two examples of where you have two series that are going to be conditional convergence then. So here, in this first one, once again, we have something that's alternating. It's the alternating harmonic series then. If we consider this series right here as is, we know that that is going to be convergence because in the last section, we said that this is an alternating series. So therefore, it is going to, it satisfies the alternating series test because it is constantly decreasing and you're alternating in terms. And the limit as n approaches towards infinity, it goes to 0. So that one is going to be convergent. But then as soon as I take the absolute value of it, the inside over here, then that becomes the summation of 1 over n, which is now an harmonic series. And that we know from the very beginning does not converge then. So therefore, this is the case where we have something that is going to be conditional convergent because one is convergent as is, but then the absolute value of it, it is not. Okay. The next one over here is kind of the same deal. This, as the series as is, it is an alternating series and it is satisfying all conditions where the limit is going towards 0. So this right here satisfies the alternating series test. So that means it's convergence. So therefore convergence. Okay. But then if I take the absolute value of it, the absolute value of -1 to the n power of n over n squared plus 1, and then you're going to get just n over n squared plus 1. This guy right here is going to be divergent. The reason is, well, you can go ahead and try the integral test in this case, and that is something that is not going to work out. So there it is. So there are some examples of each one. Now, the question is, okay, well, why do we need all of these convergence and, why do we need all of these absolute convergence all of a sudden and also conditional convergence all of a sudden? Well, that is actually what leads into this theorem over here. It turns out that if you have a series that is going to be absolute convergence, then it is technically convergent. Okay, so if you have a series that is absolute convergence, then that is going to mean that the series itself is convergent. So remember, when a series is absolute convergent, it means that the summation of the absolute value of a of n is convergent. That is what the definition means. It doesn't necessarily mean that the series itself is going to be convergent then. So that is what we're trying to prove right here. Okay, so here's how we're going to actually prove this then. So what we're going to do is we're going to take a series, right? We'll go ahead and call a of n, and I'm going to write it as the summation of a of n plus the absolute value of a of n minus the summation of a of n. So kind of like, just taking a series and then we're adding the absolute value and then subtracting the absolute value. If you're adding something and subtracting something, that's kind of like balancing the equation. So it's technically going to be itself. But by introducing these absolute value of the series in there, then that's where it's going to allow me to consider these absolute convergence things and like see how it works out. So here's what I need to do. I need to basically now show that what I have a of n over here, this thing is going to converge then. Okay, so I need to show that this whole thing converges. Well, by the definition of absolute convergence, then we know that the summation of the absolute value of a of n converges. So that means that this guy right here, that is convergent already. So that's, one part that's good. Now we have to consider the rest of the part. So here's how we're going to do that then. We're going to go ahead and say what we have right there, a of n plus the absolute value of a of n is going to be less than or equal to a of n absolute value plus a of n absolute value, and all that is going to be greater than 0. So hopefully that is it's kind of similar to what they call the triangle inequality. If you take two numbers and you add it together, the sum of their absolute values will definitely be greater than or equal to those two numbers added together, which is then greater than 0. Now, taking the right-hand side right here, we can simplify that into 2 times the absolute value of a of n. Now, keep in mind that the middle part right here is what I'm trying to show is convergent. So now I'm going to go ahead and throw the summation sign in front of every single one of these inequality. So at this point, here's what you should notice then. This right here is what I'm trying to prove is convergent. So that's going to be need to show that it's convergent. This guy right here is definitely convergent because you're just summing up a whole bunch of 0. This guy right here is also going to be convergent. And the reason for that is, well, remember, we're given that it is the series itself is absolute convergence. So therefore, itself right here, that is going to be convergent. And if you multiply by 2, well, that's convergent then. So therefore, if you're bounded by 2 converging series right here, then by the comparison test, then that means that what is in between must also be convergent then. Okay. All right. So now we get back to our original question. Why is absolute convergence necessary? Well, here's the reason why. Let's say that we have the series right here, which is going to be the summation of cosine of n divided by n squared. Now, if we were to write this out, this is what we're supposed to have. Cosine of 1 divided by 1 squared, cosine of 2 divided by 2 squared, cosine of 3 divided by 3 squared. I want to find out if it's convergent or divergent. The problem with all the tests that we've been having so far is that they either A, have to be all positive, or B, have to be alternating between positive and negative. We never actually have a test that deals with what happens if you have terms that are going to alternate differently. So in this case, here you can hopefully see this. This guy right here, that's positive if you were to just plug in the calculator. This guy right here, that's going to be negative because cosine of 2 is greater than cosine of pi, and that gives me something in quadrant 2. This guy right here, that's going to be negative because we're still in quadrant 2, because 3 is less than pi. So, and then the next one, if you take the cosine of 4 divided by 4 squared, that's going to be positive. So you see here, the part is problematic because now we have something that doesn't alternate. You have positive, negative, negative, positive, and whatever happens afterwards, it's definitely not going to alternate between the two. Nor is the absolute value of each one. Well, actually, no, we just can't deal with the absolute value for each one. But there you go. That is going to be something that we can. So therefore, a series like this, we actually cannot use any of the previous tests for it. We can't use the integral test. We can't use the limit comparison test because, all the terms are just all messed up. So this is where the absolute convergence thing comes in. So here is what I'm going to do. I'm going to show that this series is absolute convergence because if I can do that, then therefore by the theorem that we just had previously, this is going to be convergence then. So I'm going to go ahead and do the summation of n is equal to 1 to infinity of absolute value of cosine of n divided by n squared, right? If I can show that it's convergence, then we're pretty much good to go. Well, this guy right here is going to be less than or equal to the summation of n is equal to 1 all the way to infinity of 1 over n squared by the comparison test, because cosine is always going to be less than or equal to 1 in this case, okay? And now this part is good because then that means that this right here is going to be convergent. And we know this because it is by the p-series test. So this is convergent by the p-series test since p is equal to 2. So therefore, since the summation of absolute value of cosine of n divided by n squared converges, then the summation of cosine of n divided by n squared converges absolutely, which implies that it converges. Okay, so that's now the official way to write a proof where if you don't actually have alternating terms or everything that's all positive. Okay, so now we're going to use this to help us come up with one really good, I guess, test that is very commonly used. And this is what is known as the ratio test. So the ratio test, just to kind of give you an idea as to what it is, because the derivation is actually pretty lengthy and it does involve the absolute convergence and conditional convergence things. But hopefully, you know, we can talk through it and you get the idea of how it works. So let's think about how a series is supposed to converge. Your sum of each, the sum of all the terms, well, if you add them all together, it's supposed to be equal to a finite number if a series is to converge. Now, we said for pretty much all of the tests that we've had so far, if you look at each term individually, they're supposed to get smaller and smaller and smaller. So if you were to take any arbitrary term and compare it to the next term, and then you compare it as a ratio, that ratio should be less than 1. So for example, if I take, like, say, the 7th term and then compare it to the 8th term, if it were to converge, then that means that the 8th term divided by the 7th term should be something that is less than 1. And so here is the ratio test then. If you take the ratio of two arbitrary terms, and then we're just going to go ahead and take the absolute value of it because we don't know if they're going to be positive or negative. And as I take the limit as n approaches towards infinity, if that ratio is going to be less than 1, then we say that the series is going to be absolute convergence, and then therefore the series itself is going to be convergent. Now, just like the ratio thing in the geometric series test, we can look at what also happens if that ratio is something else. In case number 2, if you take the limit as n approaches towards infinity of the ratio of any two terms, the absolute value of it, and if it's greater than 1, or if it turns out that it's equal to infinity, then we can say that a of n, the series, is going to be divergent, right? Because if the ratio is greater than 1, then yeah, hopefully that makes sense. It gets exponentially bigger. Now, finally, this one's the last one right here, which is a little bit tricky. If the limit as n approaches towards infinity of the absolute value of the ratio of the two terms is equal to 1, then the ratio test is actually inconclusive, meaning that you can't actually come up with a conclusion with the ratio test. Well, you're wondering, okay, well, why is it that if it's equal to 1, it doesn't work? Because in the geometric series test, if r is equal to 1, it just diverges. Well, here is the counterexample, right? Here, you can see that we have the harmonic series over here. If I were to find out what is the, if I were to apply the ratio test, here's what it would look like. The limit as n approaches towards infinity of the absolute value of this. So that means that we have 1 over n plus 1, because that's the next term, and then divided by 1 over n. And then this part right here, the alternating part, that's going to cancel out. So this is what the ratio test would look like. Now, if I take this right here and then I rewrote it in a form that looks a little bit familiar, then that means we're going to have n over n plus 1. And as n approaches towards infinity, this has to go to 1 because the top degree and the bottom degree are the same thing. But as you can see, if you remember, again, once again, this is an alternating harmonic series, which we know is going to be convergent in this case then, okay? So that's one counterexample to show that here you have something that is that could be convergent. Whereas if I take this guy over here, the harmonic series just by itself, and I apply the ratio test, you're definitely going to get exactly the same thing, but this guy is going to be divergent. So here are basically two counterexamples to show that, yeah, you're going to get something that's inconclusive because it could either be convergent or divergent, and you're going to have to use something else besides the ratio test. So let's go ahead and apply the ratio test now to some problems, and you can see how they work. Now, before we do so, I should tell you ahead of time, when is it that you should apply this ratio test? Because, we've gone through so many tests so far. We have so many different variations. So when is it that this is going to be useful? Well, the ratio test is going to be useful whenever you see any combinations of factorial, exponential functions, polynomials, roots, and or alternating terms. So that means that if you have something that contains two or more of these functions, then that's probably where the ratio test is going to come in handy then. So here it is. Determine if the following series is going to converge or diverge. So you can see in the numerator, you have a polynomial, whereas the denominator, you're going to have a summation. You're going to have a factorial. Now, in this case, I definitely cannot take the integral of this. So that means the integral test doesn't work since I don't know how to integrate something that's factorial. It's not alternating, so that's not going to work. Comparison, well, I don't even know what to compare it to. So then that, and definitely this is not geometric. So that means now we're going to go ahead and apply this ratio test and see how that works out. So what we're going to do is we're going to go ahead and solve for the following then. The limit as n approaches towards infinity of the absolute value of the next term divided by the current term. So if I were to write all this out, then limit as n approaches towards infinity of the absolute value of the next term is supposed to be n plus 2 divided by n plus 1 factorial. That is going to be the next term. And then I'm going to take that and divide it by the current term, which is n plus 1 divided by n factorial. We're going to take this guy and simplify it as much as possible. And if I can show that this is less than 1, then that means it's convergent. But if it's not less than 1, if it's greater than 1, then it's divergent. And if it's equal to 1, then it's inconclusive. So limit as n approaches towards infinity. The first guy, well, we can't do too much. We're just going to have n plus 2. Then we have on the bottom, now I notice I have n factorial over here and n plus 1 factorial here, and I like some terms to cancel out. So I'll probably write that n plus 1 factorial as n plus 1 and then multiply by n factorial. And then on the other part, I'm going to go ahead and flip the fraction. So we have n factorial on top and then n plus 1 that's on the bottom. Note that the n factorials actually cancels out, so that's kind of good. And what we have left are going to be, well, looks like it's going to be n plus 2 on top and n plus 1 and n plus 1 on the bottom. So we have limit as n approaches towards infinity. And this part, we don't need to multiply it out because what's going to happen is you can hopefully notice that, well, we both have polynomials on both the top and the bottom. But the bottom polynomial is greater than the top. So therefore, the limit has to go to 0 because, well, the bottom is quadratic, whereas the top is going to be, it's going to be linear. So therefore, now that I show that it does equal to 0, so therefore by the ratio test, then we can say that the summation of n plus 1 divided by n factorial converges then. Okay, so that's how you're going to use the ratio test. All right, let's go ahead and try for a couple more. So this one underneath right here, you can see I'm going to go ahead and try to use the ratio test once again. And in this case, you have something that alternates divided by something that's polynomial. So again, you have two functions that are going to be just, completely different from each other. And I like to use the ratio test here because we have something that alternate, and that gets rid of the alternating positive or negative sign because, well, the absolute value just kind of kills it all off. So here we go. Limit as n approaches towards infinity, and let me go ahead and use red because I've been using it so far, of the next term divided by the current term. So let's see what happens there. So limit as n approaches towards infinity. The the current term is going to be, the next term is going to be 2 raised to the power of n plus 1. Now remember, the absolute value kills off the alternating part, so that's why we are using 2 instead of negative 2 raised to the nth power. And then we're going to go ahead and take that and divide it by n plus 1 to the cube then, okay? And then we're going to take that and divide it by the current term, which is going to be 2 to the n, and then divide it by n cubed. So very similar to what we have up on the top. We're going to take this guy and we're going to clean it up as much as possible just to see what we can get. So limit as n approaches towards infinity. The top part, we're going to write that as 2 to the n times 2. The bottom part, I can't do too much with. I can multiply it out, but I don't think that's a good idea. And then we're going to take the second part, we're going to change it as the reciprocal. So multiply by n cubed on the top, divided by 2n on the bottom. The 2 to the n are going to cancel out. So what's left is limit as n approaches towards infinity of 2n cubed divided by n plus 1 cubed. So note what I was saying earlier, that it's not a good thing to actually expand out something that's a polynomial, because all I care about are what's that called? All I care about will be the exponent, right? The power of the polynomial. In this case, it's the same thing. So what that means is if the polynomials in the numerator is the same and the denominator is the same, as n approaches towards infinity, then that means the whole thing is just going to go to the coefficient, which will be 2 divided by 1. Which is then greater than 1 in this case. So therefore, by the ratio test, we can say this is going to be divergent then. Okay? All right, so now here's the last example right here, and this one's a pretty unique one over here, actually. Again, this is not something that I can integrate or do any of the other tests to, so we're just going to literally have to apply the ratio test then. So limit as n approaches towards infinity of the next term divided by the current term. So n plus 1 raised to the n plus 1 divided by n plus 1 factorial. All that divided by n to the n divided by n factorial. I'm going to take that guy and clean it up as much as possible. So limit as n approaches towards infinity. The upper part, I think I can probably just write that out as n plus 1 raised to the n power multiplied by n plus 1. Remember, you're looking for things that are going to cancel out, so that's why I'm writing it this way. Whereas the bottom part, I can write that as n plus 1 multiplied by n factorial. And then multiply by, for the other part, it's going to be the reciprocal. So n factorial over n to the nth power. In terms of what cancels out, I see n factorial on both top and bottom, so that's good. And then we have n plus 1, they cancel out, so that's also good. So what's left now is limit as n approaches towards infinity of n plus 1 divided by n, all raised to the nth power, because, well, there's nothing else left that's there. And both of the terms that are left, they both have the same exponent. Now this part, hopefully you do remember where this goes to. Limit as n approaches towards infinity, and I'll write this in a form that would look a little bit more familiar. And by this time, actually, I think I can probably just drop the absolute values because all of these terms are going to be positive. So we can probably get rid of those, and yeah. So this part right here in the inside, let me write that as 1 plus 1 over n to the nth power. And now that really should look familiar to you. Limit as n approaches towards infinity is going to be equal to e, which is then greater than 1. So therefore, by the ratio test, this diverges then. Okay, this diverges. All right, so there you go. That's how you're supposed to use the ratio test then. Thank you so much for watching, and I'll see you guys next time. Okay, goodbye.